Okay, so 6.7 is sort of almost identical to the previous section, which was operations with vectors in 2 space, and now we have 3 space. So we just have an extra directional vector, an extra unit vector k to represent the z plane or the z axes. So we have a question here. We have 3 vectors a, b, and c, and they are represented by the addition of scales with their respective unit vectors to represent the x, y, and z direction. So if we want to find out what 2 times vector a minus vector b plus c is, we do the same thing that we did in 6.6. We take the scalar multiple of vector a and we just multiply it in front. And I'm going to break this up into components. So this is going to be with a 2 and with a 1. I'm going to write a space here, of course, plus 2 negative 3, sorry. Mistake. There's no I here, so it's a 0, 2, negative 3. And I'm going to put the C under here, which is a 1, negative 3, 2. So same thing, I have to multiply this 2 inside here and then add up all the components, all the x components, all the y components, all the z components. So I can do that in one step because I don't want to show 2 lines again. So I'm going to say negative 2, 0, and 1 is negative 1. I'm going to say 4, 2 is 6, minus 3 is 3. And I'm going to say 2 minus 3 is negative 1, plus 2 is 1. So I know that 2 vector A minus vector B plus C is this right here. If I had to find the magnitude, I could just square all 3 of them and find the square root after I add them. It's pretty straightforward. Using the actual unit vectors, we can do that as well. So I can just say that this is 2 times whatever I see in the question, negative I plus 2j plus k. Like I'm kind of already annoyed by this because I got to write a letter that I didn't need to write over here. So you can see the benefits of using component form right away. Minus vector b, which is a 0. Actually, I don't need the 0, but I'm going to put it anyways. No, I lied. I'm going to write as little as possible and still be annoyed. Okay, and plus c. Okay, so what this does is if I actually drop the brackets and distribute this inside here, I'm just collecting like terms. So while over here I have to know the position, the first number is the x value. Over here, like I have to add up all the i's. Like I can't do I and j. So it didn't make sense to put a 0 here because I know I can't add I and j, so it doesn't really matter. I know that I only have to add the 2 i's. So here, I'm going to have negative 2i. Yeah, I'll expand here. I don't know why. Sometimes I just do things because I'm bored of doing the same thing over and over. Plus 3k. Watch that mistake here. You're subtracting a negative 3. Plus I minus 3j plus 2k. And I'm going to add up all of the i's and get negative 1i. I'm going to add up all the j's and get positive 3j. And all the k's, and I'm going to get positive 1k. And I'm going to say that 2 vector a minus b plus c is equal to the same thing in component form on this side. It's like grade 9 math. So easy. Which one would you use? I don't know. Probably this one. This one looks a little bit messy, but there's some benefits to using unit vectors. It's rare to make the mistake with the 0 because the letters are different. So it's really difficult to go in that route. And I'm just going to show you one more example. Okay, so in this example right here, I have 2 vectors in 3 dimensions. There's, 3 components. I have vector A and B, or point A and B rather. It's not really a vector unless it's like OA, right? So it's just point in space, in 3-dimensional space. And I want to find the position vector OA. So from the origin to A, so all I have to do to find that is, sorry, it's not the position vector, that's actually the magnitude. Square all 3 numbers, add them, and square root it. So this is going to be 339, and this is going to be 18.41. So I know that the magnitude of OA is 18.41. Now, I'm not subtracting anything here because it's OA, so it's going to 0. 7 minus 0, 11 minus 0, 13 minus 0. So anytime you're finding the position vector with the origin, just square the numbers and you're done. Look at OB, look how easy. 4 squared, 7 squared, 25 squared. The most annoying part is I probably have to pick up a calculator because numbers are getting a little too big. It's going to be the root of 590, which equals 26.27. So the magnitude of OB is that, done. Now this is a little different. This is actually a vector from A to B. I'm not connecting them to the origin, to the same spot. I'm connecting them together. So I have to subtract their components with one another to see what the distance is. And then that vector that's connected is really a position vector with the origin after that. You can imagine it to be. So to find vector AB, I have to do 4 minus 7, negative 7, minus negative 11. Be careful there. And 25 minus 13. And that's going to give me negative 3, 4, 12. Now, this is vector AB in space. If I position that, wherever it is, and I connect it with the origin, I can now find its magnitude by subtracting those zeros, or else I would just have to do this inside that distance formula, which, is not a big deal. I could just, put brackets around it and square it. But it's way easier to just find the actual point in space and then find the magnitude. And over here I can just do 3 squared, 4 squared, 12 squared. This equals 169. Finally, a nice one, 13. Again, I've said this in the previous video, but I don't use the negatives in here because to do negative 3 squared, I know for sure that this is going to be positive. And if I know I'm always squaring these numbers, this is a waste of work. So anytime you're using magnitude, it's just the absolute value of the number. It's just a 3 squared. So the direction doesn't really matter because you're squaring everything and square rooting it to find that magnitude. Okay, and 6.7, almost as easy as, or easier than 6.6, believe it or not.